All right, so today we're going to be talking about linear approximation. Linear approximation, sometimes referred to as linearization. And the game is thus: you have a function. Whoa, look at that function. It's curvy-wurvy, Joey. That's right. So here you go, babe. Right here, x equals a. Done. But Mr. Groom, let's say this is x equals 5. Well, yeah, Joe, what about it? Well, Groom, couldn't I make a tangent line to this guy like we've been doing for the last, I don't know, couple of chapters? Sure, Joe. What would the slope of that line be? Well, the slope, of course, would be, if this is f of x, the slope would be, of course, f prime of x, right? Right? And then, of course, you could write a tangent line by y equals mx plus b. And Mr. Groom is going to write it this way. I'm going to write y equals, I'm going to write f prime of x times whatever your x is, in our case, 5, right? Right? Plus b. Now, when I do that, let me redraw that a little bit. This is going to be f of a. Is that right? Right, in this case. Equals f prime at a, that's the slope at a, times a, because x equals a, in our case 5, plus b, and then a guy could then just solve for b, right? And of course, b is f of a minus f prime of a times a. Yay, Groom, how fun. And we've done a bunch of this. It's easy. It's easy. Now, Groom, what would happen if I wanted to know what is f of 5.02? And you're like, well, I mean, I feel like I could put 5.02 into this equation. I feel like you could too. But I feel like 0.02 is awfully close to 5. That's a pretty small change, right? So in other words, this line, you see, pretty well approximate the equation. Huh? And so what we're going to do is we're going to be saying this. We're going to say f of x, rather. F of x is approximately equal to f prime of x. Darn it. Sorry. F of a is f prime of a. Now, I'm going to write it a little differently for you. What I'm going to do is this. I'm going to write it like so. I'm going to do f of a times x minus a. Okay. And then, yeah. There you go. That's what I was trying for, Mr. Groom, you big dope. Now, prove it, Groom. Well, I'd love to. Thank you. So, in other words, watch this. You recall that y minus y1 over x minus x1 is, by definition, slope. True dat, homie? True dat? And slope, of course, is f prime of x. Again, true dat? True dat. Now, specifically, what value of x? Well, we want to know about x equals a. So that would be f prime at a is equal to y minus f of a, because that would be my point. My point would be my point right here. This is the point a comma f of a, right? That's that point right there. In our case, 5 comma f of 5. But that's the game. Now keep your eyes open what I'm doing here. I'm going to multiply both sides by this guy. Yes? Nice. And then, of course, when you solve, you're going to say that y is approximately equal to f prime at a, x minus a, plus f of a, which is what I wrote a minute ago. Yay! Now, this is as long as the x we care about is close to x equals a. Define close, Groom. Well, I guess it depends, right? Bruh, because I feel like if it was right here, you wouldn't have to go very far and all of a sudden, hey, this isn't a very good approximation anymore, Groom. No, you're right, it's not. But if you were doing like the ln of a function, like this, Well, Groom, look at that. I mean, look at that. That sucker is flatter than a fritter. And it approaches that line like really well out here. Yeah, out here it sure does. In here, not so much, friend. You get over here a little ways. Whoa, it looks terrible, right? And of course, if you'd approximate it here where the slope is steeper, why, you can't go nearly as far. From it gets to be way off, yes? Because, again, steeper slopes, right? So kind of keep that in mind. So close to is a relative term. Horseshoes and hand grenades, etc. That sort of thing, okay? Now, we will be looking at this piece right here a lot. We're going to write it a couple of different ways. Allow Mr. Groom to show you one of them. We're going to call this delta x. Okay? But Groom, that means this guy here can be written as delta y, f prime of a, delta x. That's right. You're right. That's 100%. This equation and this equation here are basically the same thing. The only difference is this one, what is the change in y as x changes dx? In other words, if I change it by that much, what do you mean dx? Well, delta x. Well, like 0.1, 0.2, whatever I'm doing, right? So as x goes from 5 to 5.2, what is the change in y? That's what, just the change, not the actual value, the change. This is the actual value of the x in question, right? So maybe x equals 5.2. Okay, the difference is, this one down here, you just want to know by how much. So if you have a swimming pool and it's already this full, and you're like, oh, I'm gonna put some more water in or whatever, but putting that many more gallons in, I'm only interested in how much does the height change, right? I don't need how many gallons in the dadgum pool. I just need how much it's going to change by. Okay, but if you're feeding people, you literally need to know how many bodies are coming to dinner, right? Now, if it was well, listen, if we lower the price and we expect another 20 people, okay, well, I already know where I should have had, then plus 20, I can do the math. Literally, I can do the math. But if you're thinking about it, you're like, Grim, I just need a number. Give me an approximate number. Okay, 540 people are coming. Okay, thanks. Sweet. Perfect. So the difference really is, do I want to know the actual value of y? That would be this linear approximation. Or do I want to do this guy here, which is the change? We call this the differential. Not a whole lot of difference between the two. It's simply a matter of what do you want to have happen. Now, without a whole lot further to do, Mr. Grimm's going to just try a few, shall we? What do you think? So let's say you have this equation. F of x is equal to 3x cubed minus 6x plus 1. We want to know what's happening we want to find the tangent approximation at x equals 2. It's easy money, babe. F prime of x is 9x squared minus 6. F prime of 2 is 36 minus 30. The slope is 30. So then if you plug this guy into here, what would f of 2 be? Well, you plug it into here and you get 8 times 3 is 24. Minus 12 is 12 plus 1 is 13. Yay. So the point 2, 13 is on your graph. Are you with me? It's literally that easy. And so you're like, Joe says, Groom, you said that y is approximately 13x minus 2 plus 13. Oh, not 13. You dumbass. 30 is our slope. Sorry. That's what I said, Joe. That's easy. Well, I know. Do I need to FOIL it out? Listen, Joe, if it'd make you happy, can you? You can. Minus 60 plus 13, so 30x minus 47. If that makes you happy, Joe, go for it. Me personally, Joe, doesn't do much for me, because what I'm going to know is this. I'm going to approximate for x equals 2.15. Okay? In other words, what I'm saying here is, what is f of 2.15? Well, it's approximately. Now I plug it into here. Now watch this, friends. What is 2.15 minus 2? What, Mr. Grimm, it's 0.15. I know. Oh, I know, bro. Plus 13. Well, why are you acting weird? Just go with it for a sec, bro. This times this, 4.5, obviously. plus 13 is 17.5. Groom, why are you laughing? Well, watch this. What is slope? Slope, by definition, is what? Slope is the change in y over the change in x, right? And we normally say, like, it's slope of 3, up 3 over 1, right? Slope of 19, up 19 over 1, right? Mr. Groom, I have a slope of 7/2. All right, cool. So up 7/2 over 1. Well, no, I thought it was up 7 over 2. Same thing, right? 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 So watch this, bro. What if I take that guy, which is here, and I say that's delta y over delta x, yes? Now watch me times it by delta x. Because look what happens, bro. If this was 1, then it would just be 1 times the slope. You with me? But it's not. In our case, it's 15% of the slope. In other words, instead of going over, let's say you get a slope of, I don't know, hypothetically 30, instead of going up 30 over 1, we're only going over 0.15. Well, if we're only going over 0.15, we're only going to go up what? We're only going to go up 4.5. Okay? So if you think about that, what we're saying is this. Another way of saying that would be this. 4.5 divided by 0.15, or divided by 4. God bless. Mr. Groom can do it. I promise, friends. 4.5 divided by 0.15. If you do the math on that, you get 30. Why? Because I went up 4.5 and I went over 0.15. That's a slope of 30. Okay? Now, how good of approximation is it? I don't know. Let's get our Desmos out and have a look-see. Desmos.com. I remember what our function was. 3x cubed minus 6x. 3x cubed. Man, I miss teaching every day. Happy Christmas, by the way, kids. Minus 6x plus, what did I say? Plus 1. Plus 1. Yay. And we're at the point 2, 30. Groom, you should probably put that in parentheses. Oh. Wait, no, 2, 13, dumbass. Mr. Groom, you're stupid. That's hurtful, but you're not wrong. So watch. So I put in my equation. Now I said my equation was 30 parentheses x minus 2 parentheses plus 13. Am I right? Am I right? No, I'm not right. What just happened there? Oh, 30, dumbass. Well, this stupid. Hey, it works. Whoa, that's cray-cray. That's a pretty good fit. Yes. In the neighborhood of 2, yes? But once you get out of the neighborhood of 2, it's not great anymore. Right? In other words, what happens if you got to 4 or 5? Well, it's way off, bro. I mean, look when you're out there about 3 or 4. Whoa, you're miles away. Like miles away. So typically you're thinking, well, am I going to ask about 2.1? Yeah. 2.2, sure. 1.9? Maybe. Yeah. 1? No. I'm going to be in the neighborhood, in our case, in this case, of 2 when I do the work. Okay? Now, Groom, could I put in x equals 2 if I want? X equals 2.15 if I want to. Yeah, I suppose. And if I did that, what I would find is at 2.15, it's actually 17.9115. Yes? Does that make sense? In other words, we are, so this is close. It's close. Well, how far off is it? That's a good question, isn't it? It's a good question, isn't it? So we're going to actually take a look at that. We can actually find the error. So in our case, the actual, we said, was from the graph at 2.15. When you plug it into your original function, you get 17.91512 or something like that. And we said 17.5. Now, are we off? Well, of course we're off a little bit. Could we find about how much we're off by? Oh, sure. And so when we do that, we can actually do this. We can say, well, okay, so our excuse me, if you do actual minus, you can say predicted, you can say approximate, whatever makes you happy. And notice if I do actual minus, it could end up being negative if I want to. If I want just the actual percent difference, okay, I would just do the absolute value because it's just a rate of change. It's a change amount. You with me? If I leave the negative in there or positive, then I can either overestimate or underestimate. In our case, we're going to do 17.91512 minus 17.5. That's a positive difference already. That is, we underestimated. If I do it the other way around, I'll overestimate if I get a negative, okay, when I subtract, okay? And so what I do there is I take that error and I just divide. We're going to divide by the actual value. Oops, I wrote it up here. Divide by actual. And then we're going to times by a percentage, by 100%, so that we can get a percentage of error. So 17.91512. And then times 100, of course. So, clear. 17.91512 minus 17.5 is that divided by 17.9. So that's about 2.3%. 2.3% error. Is that pretty good? I feel like that's pretty good. You got like a 97.7% on your test there, Joseph. That's pretty good. Attaboy. Not bad at all. Not bad. All right, let's try another one. Give me another one, Drew. Well, all right. If you insist, bud. What if we take the natural log of 2x? All right. And what do you want to do it at? Well, I would like to, by God, do it at x equals a half. Because, sure. Well, that's weird, Groom. When you plug it in, you get f of a half. Well, 2 times a half is 1, right? And the ln of 1 is es cero, senor. Es cero. Si es cero. And so if a guy's doing this, you're like, oh, well, I probably need to take the derivative here. So f prime is going to be 2. Well, it's going to be 1 over 2x. That's the derivative of the outside function, right? Times the derivative of the inside function times 2 is going to be 1 over x. Okay? It's 1 over x. And so, oh, okay, well, that's cool. That seems reasonable, I guess. Sure. And so if I'm doing this, I go, okay, well, add a half then. 1 over a half, f of 0.5. Prime of 0.5 is 1 over 0.5, which is es dos. Si es bueno. So y is approximately equal to 2. X minus 0.5 plus 0. That's easy. Let's see, that looks reasonable to us. Clear. ln nice, there he is. Yay. And s I want the point 0.5 comma 0. Oh, there's a 2x in there, stupid. Nice. I know what I'm doing. Good for me, Joe. Nice. Now, Grum, you're saying that y equals 2 parentheses x minus 0.5. Oh, nice. Grum, could I use this equation to predict what's happening over here at x equals 2? X equals 2. Bro, no. As you can see, they are miles apart from one another. Miles apart. Lord have mercy. That prediction versus this actual, that's ridiculous, sir. What are you talking about? Grum, what about if I just did like, I don't know, like 0.83 or something? Yes, I feel like we could probably get away with that. You with me? We could probably get away with that. So you guy would come in like this, x equals 0.83. So then f of 0.83 is approximately, it's going to be 2 times. Now 0.83 minus 0.5 is 0.33 last I checked, yes? And so 0.66 roughly. Boom. Well, if a guy comes over here and does that on his calculator here and goes, oh, wait, there it is right there. It's right there. 0.66. Shut up. Green, was that bigger than the actual? It sure is. Is it off by a bit? But it's off by a bit. It's off by a fair amount. 0.506. Good enough for government work. Divided by 0.66. Oh, not divided by, you dumbass. Minus 0.66. Notice that that's negative. If you want to, you could actually leave the negative in there. It tells me that you overestimated. But you don't have to. You don't have to do that. If you don't choose to leave it in there, then you're just getting the actual percent difference. But it's not a negative difference. Negative just means, of course, that you've overestimated. I'm going to subtract them backwards because I want to be positive just for fun, if that's okay. Otherwise, I have to do an ABS, and that's a whole thing. And it's too late in the day, kids. By the way, I'm just enjoying my summertime. 30%, good Lord, 30% off, bud. That's terrible. Terrible. You're off by, bro, you got a 70%, dog. That's terrible. You know what I'm saying? So how close is that? Well, it's out there. So I would say that it's too far out. So is it possible? You're like, I don't want to predict that. I want to do for x equals 0.45. Sure, if you want to do that, it's the same basic premise, yes? And so in our case, of course, it's going to be y is approximately 2. And then, of course, if you put 0.45 into here, you're going to get negative 0.05. In other words, it's going to go down because, again, as you go this way, you're going down the slope, yes? Assuming that our slope, in our case, our slope is 2. We'd be going up and over. If it's positive, we're going back and down, yes? And so that makes sense. So negative 0.1. And so if a guy comes in here and does this, put in 0.45. Oh, look at that. Oh, it's like I know what I'm talking about. Shut up. Oh, whoa. They're literally almost on top of each other. They are. But again, I'm overestimating, aren't I? And so actual minus predicted divided by actual times 100%. Calculator. So be careful. Actual negative 0.1053605 minus a minus 0.1. Don't screw that up. Divide by negative 0.10505. As you can see, we're at about 5%. That I can live with. You with me? 5%. Negative because, again, I overestimated. Okay, my prediction was higher than what actual was. Again, if you just wanted an actual percentage, then it's 5% off. Okay, that makes sense. The negative just tells me, did I over or under approximate the thing? Okay, let's do another one. We can do this, bro. We can do this all day long, bro. Oh, yeah, we should do one of those just for fun. So let's suppose your f of x was all right, so x better not be what, like -2 and -1, I guess, yeah. But we're probably gooch at 0, yes? So Mr. Groom's interested at 0, just for a good time, okay? So I'm going to create a linear approximation, or I'm going to make the linearization at x equals 0. By the way, that's my tangent line. That's all we're doing. So don't get all, I don't know what to do. Is it first semester calculus? Yes. Did you take a derivative? No. Then you're doing it wrong. Okay, there you go. Why don't you start with that? Minus top times the derivative of the bottom. So x squared minus 3 over over x squared minus 3x plus 2 squared. That's hot. Again, I'm only interested at 0. So as you can see, f of 0 is negative 3. If you put 0 into here, you're going to get a dos minus, and then this is going to be this will be 18 minus 18 though, so negative 16 over 4, which is negative 4 slope. Nice. Again, plug it in 0. Done. Oh shit, that's actually not even going to be that, because it's going to be, hold the phone, bro. Hold the phone. It's actually not true. It's going to be just negative 18, because this is going to go to 0. So it's just negative 18 divided by 4 with negative 4.5. Negative 4.5. There we go. Yay, there's our slope, Mr. Groom. Okay, so that means that if I do this, I can say that f of x is approximately negative 4.5 x minus 0 minus, so plus a negative 3. Okay? Let's see if that looks right to us. X squared minus 6 divided by x squared. No, darn it, x squared minus 3x plus 2. That's hot. Bam. There you go. Nice. Whoa, we're interested at 0. 0, comma, negative 3, sorry, negative 3. Oh, whoa, that's hot. And then, of course, my equation is negative 4.5 parentheses x minus 0. Don't need the 0. I'm going to leave it there. Don't cry about it. Bam! Oh, dude, we rock. Oh, my goodness, we rock. We rock. Now, Mr. Grimm wants to predict for x equals negative 0.2 or something. So what happens when x equals negative 0.2? Okay. Notice that delta x is also negative 0.2. Am I right? Make sense? It's also negative 0.2 because we went in the negative direction. Okay? And so we plug it in. It's the same thing. So if you plug this into here, this piece here, which is delta x, just becomes negative 0.2. Well, listen, friends. If here's your function and here's your tangent line, hey, my tangent line is a negative slope. That's hot. So when I go positive direction, I go down. True dat, homie. When I go negative, I go up. And so the change is going to be positive. So this times this is your change in y. And so it's negative 4.5 times negative 0.2 minus 3. And so this is positive 0.9. So it's negative 2.1. In other words, as I came back here, I went up, and I went from negative 3 to 2.1, negative 2.1, right? And let's see if that's true on the graph. So x equals negative 0.2. Oh, shut up. Give me look a mile apart. Bro, I zoomed in. It's going to be just fine. So again, we are overestimating. So if I care about the positive or negative, okay, then I want to make sure I use an absolute value, right? But I'm always going to take the actual minus the predicted divided by the actual and I get about 21% difference. Is that right? Yeah, I guess. No, you buffoon. It's 2.25, you freaking goof. What a goof. Let's try it again. Huzzah! Divide by, oh poop, negative 2.25. There you go. 7,576. And you get, 7%. That, my friends, makes more sense. That's the sort of thing that you'll be doing as we get into this, what we call linear approximations. That's what we're doing. Okay. Now, tomorrow, I'm going to spend a little more time on this tomorrow. We're going to hit a few of these, of course. Groom, I do I have to do derivatives? Yes, for God's sakes, of course. Now, what you will also be doing tomorrow is this. You can be finding something like this. Suppose you have, and we'll do this tomorrow, so don't get all panicky and weird right now. So just calm down, bro. I got you. We'll do a nice boring one here. This is our guy, and then let's do x equals 2, sure. And I want to predict, okay, that's fine, let's just do that. So then f prime is 4x minus 3, of course. That means that f prime of 2 is 5. That's our slope. And f of 2, it would be 8 minus 6 is 2 minus 1. How about that? So it means the point 2, 1 is on my graph, and my slope is 5. So I'm just going to write this down, y. So I can write like this, y is approximately 5x minus 2 plus 1. That's true. But another way of writing that would be to write delta y is approximately 5 times delta x. You with me? That's just a different one. Because this is delta x, and if I subtract this back to this side, it's going to be y minus y, right? Okay, this is what's referred to as the differential. So what I want to know is this. What is the change in y when I go, what's the change in y when x is 2, when I move to the right or to the left a certain amount? Well, in our case, I want to go from 2 to 1.91. So that means my delta x would be negative 0.09. You with me? I'm just going to plug that in. I did it in my head. Bloop. Because 1.91 minus 2 is that negative 0.09. And so if I do that, what's that tell me? Well, it's going to tell me that negative 0.09 times 5 is negative 0.45. That's just telling me that I expect my y to decrease by negative 0.45. Okay? Can I prove it? Yeah, I feel like I can. So watch this. So if I go y equal poop. My equation was 2x squared minus 3x, 2x squared minus 3x plus 1 minus 1. Okay, and I'm interested in x equals 2. Not 2 equals 2, you moron. X equals 2. Oh, yeah. There you go. Cool. Hey, that's cute. Nice. Now, let's go. Oh, shoot. Let's go over to x equals 1.91. Well, look at that. So here we are. We're at 1. Here we are here at 0.566. Well, I don't know that math in my head, Groom. I feel like you do. Watch this. What is 1 minus 0.5662? Oh. Well, okay. Excuse me. It looks like, and we should have read it the other way around, 0.5662 minus 1. It looks like we went down 0.4338, which is awfully close to what, friends? Negative 0.45, you with me? And so that's the thing we will be doing with differentials. Again, don't care what it actually is. Just want to know, hey, there's a change. How much did it change by? Okay, so we got tomorrow. I want you guys today to focus on finding, I want you to work on finding the linear approximations. And in this first section, you're going to find linear approximations, and specifically in the linearization. And so I want you to really focus on the first. Come on, Jay, you got this. So I really want you to focus on problems like 9 through 12. And then also 45 to 54, those ones right now. Those are the linearization ones. And I want you to focus on doing them. Linearization / linear approximation. Tomorrow we'll spend some more time going over the differentials. A lot of kids freak out about it. I know personally when I was a young man, because I wasn't smart as some of you, like Devin, brilliant kid that she is. And Darcy, God bless, I'm not even close as smart as Darcy is. But anyway, I struggle with differentials. I don't know why. I just did. But again, it's not hard. It's the same thing. The only difference is, it's the change. I'm not adding the original y value to it. I'm just going, well, forget about where I was. I'm going to go up or down this much. That's that's just the amount of change it is. And that's just the only difference between the two. Again, it's how much did it change? I added, the height went up two inches or something or whatever. I don't care. There's a difference between that and 15 more people are coming to dinner. Okay, cool. Versus 15 more people are coming to dinner. Well, how many did you expect initially? Because it matters, right? If I was expecting 1,000 people and another 15 people are coming over, I'm not changing anything. I'm not changing anything except the number of place settings, of course, I guess. But I'm not changing anything because if I'm cooking for 1,000 people, there's already plenty of food for 1,015. You know what I mean? I'm not worried about it. If all of a sudden I had to get another 600 people, oh, geez, that matters. If I was planning an intimate dinner for 5 people and you saying now there's 15 people coming over, Judas, 15 more people coming? Are you kidding me? Are you kidding me? Because that's what it's about, right? So if I need to know how many people are coming total, again, that's linear approximation. If I want to know the difference, well, the difference between what? Well, what I expected, and then a little bit more. Something's changed, yes? And so that's the difference between these two things. Now, we're going to spend some time again on this in the next couple of days, so don't panic. Have some fun with it.